those above for one moment. At the end of that time, if nothing happens to your submarine, yeah, that's a big if, isn't it? The cyanogen gas in the world will have spent itself. Then, if all people in the world have perished under the deadly gas, you can claim the world for your own. This is the ad now. If they are not dead, perhaps you can stand the laugh. But were we any smarter than the last time it came by? No, we were not. There were thousands and thousands of factions that said that the reason that we had the shuttle disaster was because Halley's Comet was in the sky at that time too. But it's not just Halley's. There's plenty of comets going around. In Hevelius, back in 1665, all these are different comets. And look how, and he was a scientist of the time. Okay, people looked up to him. These are the way he depicted the comets that he knew about. And they all look like swords, don't they? And so he associated all comets with war. Comets always associated with bad weather. And the thing you have to remember is this still is going on today. Not as much overall in the percentage of the population. One of the interesting things is that Halley's Comet was in the sky when Julius Caesar died. And they actually depicted a coin with his face on one side and Halley's Comet on the other on the year that he died. And then we've got droughts, famines, all sorts of, weird happenings, deformed animals. And the Great Fire in Chicago in 1871, the Great Comet of 1870 was in the sky. They blamed it on the comet. And then, of course, we go back to Hale-Bopp, Mr. Applewhite. This is the picture I wanted you to see. This is from Hubble. This one over here on your left is a wide field view of Hale-Bopp comet with Hubble. And this is a close-up. This is the picture that started all the furor. When NASA announced that they had found the secondary object, and by that they meant a piece of the nucleus of the comet, following in the same path as the comet, Mr. Applewhite decided that's the sign he had been looking for, and announced that that was the UFO that was going to destroy the world so that we would have a second coming, and all the people that had perished under his hand would be accepted in the second coming. So we have these things still today and today. And this is actually something that's out on the internet right now. The comet is coming, and we're going to blast it out of the sky with a comet book positron. So now let me tell you a little bit about the reality of comets, some of the things that we actually do know about, facts and figures. Again, back in as early as recently as 1820, 1850, we assumed, or most people assumed, that comets were part of the atmosphere. They were just hanging in our air. In reality, comets come from deep space. They're part of our solar system. The solar system that we have right now is nothing special in space. There are probably solar systems everywhere. We have a sun, which is an average-sized star that happens to be one of almost 300 billion in our own galaxy. Our galaxy is something that we call the Milky Way. And the Milky Way is a huge spiral if you haven't seen it in pictures. And the sun goes around in it seems like an infinite circulation around the center of the Milky Way galaxy. Our sun's nothing special. It's just a medium star, about 7 billion years old, about medium age, and it happens to have planets. And most stars probably that are not part of a double star or triple star system also have planets. So planets are not unusual. We're in a tiny corner of the Milky Way galaxy, which is our own galaxy. Most of our solar system is empty space. There's nothing out there. You go from one planet to another, you encounter a lot of blackness, a few atoms, and that's pretty much it. Some cosmic stuff and maybe some meteorite dust, and that's it. We have one average star, 9 large bodies that we call planets, lots of solar system garbage, which are the asteroids and meteors, and then we have trillions and trillions of comets. Comets are not special. They are commonplace. They're the most common object in the solar system. When I first started studying astronomy and lecturing particularly, the most common question, why do comets come our way? When they would learn where they come from, and there's a reason for the question if you're in a group of physics students, and you're talking about the static nature of where comets come from, the first question is, how do they get out? And so I invented the comet giant. We have this big giant out there slinging comets our way. And, really, for lack of a better reason, it's as good as anything anybody else can come up with right now, because we don't know, but we have some ideas. The comets all come from a cloud of debris that's about 12 trillion miles away. It's a 1/3 of the way to the star Alpha Centauri. It is a donut. that surrounds the sun. It orbits the sun very much like the rings of Saturn orbit that planet. You can see this is not to scale, of course. This is 12 trillion miles out here, which is getting close to a light year. But Pluto is well inside of the orbit of the Oort cloud. Looking at it a different way, and this also is not to scale, the fringes of the impact of the sun, the ability of the gravity of the sun to hold even a slight hydrogen atom diminishes right here. The comets are way out here. They're about 1/3 of the way, again not to scale, to our closest star, Alpha Centauri. Now, we don't know how, we think that the comet cloud, the Oort comet cloud, is a debris cloud left over from the formation of the solar system. We're not absolutely certain about that, but that seems to be the case. And one of the reasons being is that you take an average comet and you look at it and you weigh it and you cut it and you play with it, which we haven't really had an opportunity to do, and it resembles very much either the gaseous planets like Jupiter, Saturn, Uranus, and Neptune, huge planets without a solid surface, or it resembles the terrestrial planets like Earth, Mercury, Venus, and Mars. And they do get out. When they get out, they will never return to the Oort cloud. Once they come in, we have two different types of orbits that are established for a comet. A long period comet, and we'll talk about that, and then a short period comet. All long period comets end up being short period comets. This is stuff you really don't need to know too much about, but the short end of this story is that as a comet comes in, we used to think there was such a thing as a hyperbolic comet, which meant it came in from deep space and it circled the sun and it went back out into deep space and it would never appear again. That is not the case. That was as recently as 1971. We know now that comets that come in from the Oort cloud, there are no comets in deep space. If they are, they're renegades. They somehow have just ended up out there. Most of the comets come out of the Oort cloud. Comet ISON is an Oort cloud comet, and that's very special and something very important to remember. An Oort cloud comet is a fresh comet. It has never been exposed to sunlight before. Hard, direct sunlight. Certainly feeble sunlight at a distance of 12 trillion miles. The interesting thing is out there where the comets come from, it takes tens of millions of years for ISON to have left the Oort cloud and make it all the way down through traffic in our solar system and finally get to where we have it today. It's been on its way now for probably 25 million years. And that in itself to me is remarkable. Once the comets pass the sun, as they come in, they begin to accelerate. The sun's gravity is huge. It's the largest thing in the solar system. And it accelerates them to gravitational forces, and they literally slingshot around the sun, and they're passing as fast as they can go at that point, and it slingshots them, curves them back into space, but the orbit is captured. Once that comet goes around the sun, it's locked in, and it's going to have that orbit until something big, like Neptune, Uranus, Saturn, or Jupiter, is big enough and gets close enough to it to perturb it to where it can't go back out any further, and it begins to close its orbit up. And then it becomes a short period comet, and it'll come back much quicker. It makes perfect sense to look at the yellow line, and you realize, just taking trips, it's going to take a lot longer to get back to us. Halley's takes 76 years to make a complete round trip, than a short period comet, the one in the pink line there. We have one comet called Comet Encke, which is in the sky right now. It's absolutely beautiful. It is the brightest comet in the sky, the early morning sky right now. And it's barely naked eye visible. And it has the shortest of all orbits of a comet, 3.3 years. Every 3 years it comes back. It doesn't put on a good show every 3 years, but this year it is. It's green, it's beautiful, has no tail. It's just a big old glowing green ball in space. Comets basically are made of we have three components physically of a comet. We've got the nucleus, which is the very center. It's the stuff of a comet. Remember I said Halley's had a nucleus of 6 miles across. ISON has a nucleus of 3 miles. So it's a much smaller comet than Halley's. And Cohete, by comparison, also had a 3.3 mile nucleus. The coma is simply the head of the comet. That's the glow of gases that outgas from the small nucleus. As it gets close to the sun, it begins to glow and outgas, and it can get quite large. And then we have tails. We have one that can be a dust tail, which is a bunch of stuff and debris that's streaming off the comet that follows the comet in its path. And then we have the ion, or the gas tail, which is when we turn on the lights, most of them are fluorescent lights. And there's a big difference between an incandescent light, like the old-fashioned light bulb, and a fluorescent light. A fluorescent light glows from the energy from two electrodes at the end of the light bulb. And it excites the gases, and they begin to move, the electrons begin to move rapidly, and it glows. The more energy, the higher it glows. High-pressure sodiums, for example, have a higher glow rate than a low-pressure sodium. And so the energy from that is what makes that glow. It doesn't actually have a filament in it. And a comet is the same way. The big tails that usually develop are ion, are gas tails, and that's why they're so important to us. And they're filled with all kinds of good stuff. This is just basically how comets develop. Around the trip, about 5 times from the sun, which is about 500 million miles, which is almost the distance of Jupiter from us, the head begins to form. The actual circular part, the outglow, the coma of the comet begins to form. And about the time the comet gets to the orbit of Mars, about 100 to 150 million miles away, we begin to see a slight tail forming. ISON, and this is why people got excited about it early, we discovered ISON out near the orbit of Uranus, which is much further. I mean, we're talking about 750 million miles. No, that's not even right. 2.5 billion miles. And by the time it had reached there, it already had a little short tail. And it was already quite bright. So just extrapolating, we thought, well, that's brighter than anything we've seen out at that distance, so it's going to have to be a pretty bright comet. Partially that's held up, partially it has not. The nucleus of the comet, as I said, is a very, very tiny object. Just look at the contrast here. This is Comet Holmes. As a matter of fact, I saw some nice photographs of Comet Holmes before we started that some folks here had taken. Where you see this globe, that's what we call the head or the coma. I'll talk about it in a second, but there's the nucleus. That little tiny substance that somehow or another survives all these intense trips around the sun. As the nucleus warms, you can see two things happen. You've got the solar wind coming, let's just say, from the top up here, and then the comet's moving this direction right here. So there's a lot of intense forces on the comet. I won't go into a lot of this, but what is happening here is that both of these factions will cause the comet to eventually begin to rotate. And I wanted you to see this because the latest news on Comet ISON that I got last night is that the comet is not rotating right now, but is about to, and that's very significant in terms of the predictions. Basically, there's 2 types of comet nuclei, and that, again, that's the stuff of the comet. I did a lot of research in the early 70s on this, and I think that we're pretty much locked into 2 different models. We have an ice model, which some people call the dirty snowball model, and we've got a little planet model. Comets probably got formed into 2 different ways because way back about 3.5 billion, maybe 4 billion years ago, our sun, which was probably a fairly young star at that point, passed or crossed paths with an evolved reddish star that was very carbon heavy. As they get older, stars begin to develop in their cores heavier materials like helium, which eventually goes into lithium, which eventually goes into carbon. And these heavier elements are literally the building blocks of life by the time they get into an environment where such can happen. And probably if the 2 stars did pass, passing in the night, their wakes between the two gravities pulling on each other, literally pulled gases from each one, and probably created not only comets, but perhaps the planets that we have in the solar system as well. So the comet formation is probably coincident with the formation of our very Earth and all the planets that we see. Studies that I've done on comets in the past reveal that we have all of these different components in them. All of these percentages for all of you scientists out here, this is in relation to the abundance of water. But nonetheless, all of these molecules are in a comet nucleus. Some of them are very, very significant because they are the building blocks of amino acids. And they're very prevalent. You can see starting at the top of the water, that's the most prevalent molecule in there, and then you go all the way down and you see the hydrogen cyanide, that's the cyanogen. So all comets have this stuff, and then we have these rare gases, which essentially are very volatile gases that once again glow when they're exposed to energy, and that's what gives them the bright tails. That's just to let you know that all comets kind of are pretty much the same, but interestingly, almost all comets are water. The ice model of a comet, one type that we have two types, remember, a planet type and an ice type. The ice type probably do not have an outer edge. They don't have a crust like the Earth does. So when they go around the sun, they're very quick to react. As soon as they begin to get some energy out of the sunlight, they begin to glow. Something with a hard rocky crust around it is not going to do that. So the planet model probably would have a hard, rocky, thick, not volatile crust that would have to be burned through to get to the good stuff on the inside to make a good comet. Does that make sense? Comet Kohoutek in 1973 had a crust around it. We actually know that now because we saw carbonaceous compounds spectroscopically being reflected in our telescope. So we were able to actually ascertain that it did have something very, very hard and rocky around it. So it didn't have enough time to burn through. What this is showing you is that if there are cracks in it, if there are fissures where something can get through and the energy can get in, you're going to have a little bit of activity out of the comet. This is a close-up of Halley's Comet taken in 1985. This was a spaceship, not an Earth-based telescope. And this is an actual photograph over here on the right, and here's a sort of a map of what we're seeing of it over here on the left. And, you know, just from that one picture, we can determine an awful lot about this comet. One thing that you notice, it looks like a potato. And, you know, this is the most famous comet of all times, around, you know, every 76 years, all the way back to 3000 BC maybe, and they had potatoes then too, so they probably thought if they saw it, it looked like a potato. But notice the places where all the activity actually emanate, from these craters and fissures. And sure enough, in the picture you can see all of this outgassing. And the one thing to keep in mind that 88 to 95% of that is water. It's pouring out 800 tons a second in water. This is right after it passed the sun, and look at that vaporization. It is just glowing. And unfortunately, in 1985 and 86, any of you that took the time to go out and look for Halley's Comet were sorely disappointed. It was not a good comet. It was one of the poorest showings that it had ever had, and it broke apart. It actually is two pieces now, and we don't even know if it's going to return for the next trip. Another comet that we photographed up close by the Epoxy spacecraft is Hartley. And this is one that I watch regularly from the observatories in Arkansas. We can't quite see it this well, but look at the gases coming out of it. I mean, they are a little bit spooky to look at it. And from that, NASA has compiled this little artist's rendering of what it probably looks like if you were hovering above Comet Hartley's core right now. Little fissures, geysers of water coming up, outgassing from the center of that comet. The nucleus, for example, in Comet Home, 7 miles across. Every bit of that comes, this entire comet, 1 million miles across. That's as large as the sun, larger than the sun, actually. 1 million miles across comes from something only 3 to 7 miles across, and it can make something that spectacular. And then the comet tail, that's what everybody wants to know about. What kind of tail are we going to look at here? What's it going to do? Again, we have two types of tail, the solar wind, which is the pressure that you feel from the sun. When you go out in the sun and you sunbathe or you're mowing grass or something, and you can feel the heat radiating on your forehead, you know, you think, oh, I'm really getting hot. It just feels like a really hot day. If you actually stop, your body is very perceptive, by the way. If you stop and actually tune in to what you're feeling, you can literally feel sunlight hitting your skin. I think some of you know this because I hear people say, man, it just feels like it's just bombarding my skin today. What's going on? It is. It's photons. You're actually feeling the bombardment of particles of light hitting your skin, exciting the nerve endings in the skin and the sensory parts of your body. Solar wind has a tremendous influence all the way through the solar system, and it's going to make that ion tail. The tail's flying toward A over here, where the comet is, and it leaves a dust tail in its wake. That follows the comet. The ion tail does not. Now this is, we're rushing ahead. This is Comet ISON probably in early December, okay? And the only reason I put this in is I want you to see how the tail angle changes. Now here's the sun. Let's just say this is the same time every night, December 13, 14, 15. And notice how the tail angle is changing so rapidly. But notice also that it's always pointing directly away from the sun. That's because the solar wind is pushing that tail. But the comet is moving this way. So if the comet breaks apart, which it may, it will also have a dust tail, which means we'll have two tails. If it has a dust tail, you've got this tail, which will definitely be there. That's the glowing gas tail. That's the one from the fluorescent light energy. The dust tail will be following the motion of the comet, so it's going to be in the wake. In other words, down this way toward the horizon on each of these. So it follows the path and will actually trace backwards the path of the comet from where it's just been. Famous tail comets. The Kiyosaki of 1965 was the greatest one of all times. The tail stretched almost 180 degrees, almost all the way across the sky. It was visible in broad daylight. You could go out and block the sun, and you could see the tail from one horizon to the other on several different occasions. This is more recent. This is Comet McNaught. We didn't get a chance to see this in the northern hemisphere. This is the southern hemisphere for you astronomers out there. Of course, that's the Milky Way, the small Magellanic Cloud, and the large Magellanic Cloud, which we never see up in the northern hemisphere. The Comet McNaught was absolutely spectacular. It could easily have been the comet of the century, but nobody saw it. I want to show you this because this is, whoa, what happened here? Just hit the wrong button. There we go. These are interesting. This is Comet Pan-STARRS. This is in the sky right now, and it's something we're keeping up with at the observatory. This is early on, and it was a very, very bright comet, almost up close to Polaris, the North Star. So it was in the sky all night long, easy to see. Naked eye, binoculars would have showed it. You know, people just didn't know where to look. It came by so quickly, we really didn't have a chance to get much word out on it. But you see this long streak of a tail, looks like a pencil mark going all the way up. That is the gas tail. That's the ions that are flowing out from the solar wind. And this little bitty stubby thing right here, that's the dust that's being left behind from the comet's moving. So what direction from where you're sitting is the comet moving? Upper left. Upper left. So the tail, the horse, the cart's preceding the horse here. The comet's actually going this way. The sun is down here pushing that tail out, but the comet's moving this direction, leaving this little bitty bit of dust. But we didn't know how remarkable it was about to be when this picture was taken, because the comet was turning very sharply around the sun, and 2 weeks later, look what happened. We still had the ion tail. Now it's pointing straight up. The sun is down here. This was taken about midnight, so the sun was below the earth and shooting straight up. But because it was turning, look at the expanse of the dust. This thing was a very, very dusty comet. It was giving off all kinds of particles. And sure enough, the comet pretty much disintegrated after these photographs were taken. Some comet tails fan out and are simply fan tails, and it happens to be a combination of simply the angle that we're looking at them, as well as the energy of the comet itself. Some comets have both, and this is what we expect out of ISON. This is the dust tail. We see it